Hi everyone. So this is the Math 22A Linear Algebra Quiz 1. I'm just going to work through the problems so you can kind of see my thought process for these problems and check your answers and see what you may have missed. Okay, so the first line here is pretty helpful. It says, we saw in class that the derivative operator is linear. The second derivative operator is also linear. Okay, so right away I tell you that the operator or the function that we're thinking of is the operator that takes the second derivative. So here we already know that the vectors we're going to be acting on are functions that we can take the second derivative of, so twice differentiable functions, and that the operator that is acting on them is the second derivative operator. So the first problem asks us to write down the two or one combined properties of linear functions, additivity and homogeneity, for an arbitrary linear function L and vectors u and v. Use c and possibly d to represent scalars. Okay, so here I tell you that the vectors, I want you to represent them with u and v, and then we're going to use c and d to represent scalars, and then the operator or the linear operator or the linear function is L here. So the two that we know define linear operators or linear functions or linear transformations, all of these words are equivalent, says additivity. So the first one is additivity. Additivity says that L of the addition of the vectors is the same as the addition of L of the vectors. Okay, so L of u plus v is equal to L of u plus L of v. That's the first requirement for something to be linear. The second one is homogeneity, which says that L of a constant multiple of a vector, so L of cu equals C L of u. Okay, so the constant multiple times the image of L under the operator L, or the image of u under the operator L. Okay, now the one combined that we discussed a little bit is that L of cu plus dv is equal to C L of u plus d L of v. Now this set of two requirements is exactly equivalent to this one requirement and vice versa. So you only had to write down either this pair or this one. You had a choice. Okay, now it says write down these same two or one properties for the second derivative operator for arbitrary twice differentiable functions f and g, use c and d to represent scalars. So here I tell you, represent your vectors, which in this case are twice differentiable functions, with f and g. The operator, which above we called L, is now the second derivative operator. So literally all you have to do is everywhere you see u in this, write f of x. Everywhere you see v, write g of x. Replace the vectors in our linearity properties with the vectors in this situation. Replace L with the second derivative operator, and c and d are still just scalars. Okay, so we have a choice. We can either write down these two properties. So linearity for this in this situation says that the second derivative of f of x plus g of x, the sum, is equal to the sum of the second derivatives. Okay, so that's additivity. Now homogeneity says that the second derivative of c f of x is equal to c times the second derivative of f. Okay, or you could write down these properties combined. So the second derivative of c f of x plus d g of x is equal to c times the second derivative plus d times the second derivative of g. Okay, so again, or you could write these two or this one, and these two or this one. They're exactly equivalent. Is what you wrote down in problem 2 true for twice differentiable functions? Well, of course it is. We know that the second derivative breaks up across addition. So when you take the second derivative of the sum of twice differentiable functions, it's the same as the sum of the second derivatives of those functions. And we know that this is true. This is just the constant multiple rule. So yes, we're using the sometimes called the sum rule and sometimes called the constant multiple rule. Okay, so now we're going to think about how this linear function or linear operator acts on cubic polynomials. Consider an arbitrary cubic, which we represent as ax cubed plus bx squared plus cx plus d. A, b, c, and d just represent the coefficients of the polynomial. And I told you that we're going to represent this polynomial by the vector a, b, c, d. So I say we're just going to think of polynomials instead of as polynomials as vectors of just the coefficients, right? Because once you tell me the coefficients of a polynomial, I know exactly what polynomial it is. Now this one, I say, what is the second derivative of this polynomial? This is just actually like a calculus problem. I want you to literally just take the second derivative. So when you do that, you'll get 6ax plus 2b. Okay. And then I say, how would your polynomial answer from problem 4 be represented as a 4 vector, given our choice of representing this polynomial as just the vector of its coefficients? Now a little bit tricky thing here is that I tell you we put in the first spot the coefficient on x cubed, the second spot the coefficient on x squared, the third spot the coefficient on x, and finally the fourth spot the coefficient on 1. Now here in our new polynomial, this derivative polynomial, the coefficient on x is 6a, right? So that goes in this third spot. The coefficient on 1, 2b, goes in the fourth spot. The coefficient on x cubed here is 0, and the coefficient on x squared is also 0. So your vector, given what I told you here, has to be 0, 0, 6a, 2b. Okay, now notice I named this v. So then I say, thus our operator maps the vector a, b, c, d to v, this vector 0, 0, 6a, 2b. What 4x4 matrix satisfies this equation? So notice I'm replacing here, v is exactly what we got before, 0, 0, 6a, 2b. Okay, so the first row, I want a vector that when I dot it with a, b, c, d, I get 0. That's going to have to be the all zeros vector. It can't be anything that depends on this vector, otherwise it's not a well-defined matrix. Okay, again, now I want another vector that when I dot it with a, b, c, d, I get 0. Has to be the all zeros vector. Okay, now I want a vector that when I dot it with a, b, c, d, I get 6a. This has to be the vector 6, 0, 0, 0. We have to get 6 times a plus 0 times b plus 0 times c plus 0 times d. Okay, likewise, this vector that when I dot it with a, b, c, d, I get 2b, has to be 0, 2, 0, 0. Okay, so now I've filled in my matrix. Problem 7 says, write down an equation like that in problem 6, which is equivalent to the differential equation above. It should involve your matrix from problem 6, the vector representing p of x equals just an arbitrary cubic polynomial, and the vector representing 18x plus 4. So first of all, the vector representing 18x plus 4 is going to be 0, 0, 18, 4. For the same reason we got this 0, 0, 6a, 2b, the vector, has coefficients 0, 0, 18, 4. 0, 0, 18, 4. Okay. Now, when we take the derivative of p of x, so here p of x we're representing as a, b, c, d. Now when we take the second derivative, we now know that this is equivalent to just multiplying this vector representing p of x by the matrix that we figured out up here. So 0, 0, 0, 0, 0, 0, 0, 0, 6, 0, 0, 0, 0, 2, 0, 0. Okay, so this is the matrix that represents the second derivative. This is the vector that represents p of x, an arbitrary p of x. And then this is the vector that represents 18x plus 4. Okay, so this equation is exactly equivalent to this equation. Write the augmented matrix for this system of equations. So the unknown here is the solution p of x. We're looking for the polynomial that satisfies this differential equation. which really all we need to know are these coefficients A, B, C, and D. So we're looking for this. So our augmented matrix just takes this matrix A and this right-hand side B, and it forms the augmented matrix with A on the left-hand side and B on the right-hand side. Okay, now I say perform elimination to get your solution. Don't worry if your matrix makes this quite easy. Be very careful that you get your augmented matrix into RREF, row reduced echelon form, otherwise your solution is hard to read. So what I meant by that is make sure that you, in row reduced echelon form, will have all of the non-zero rows at the top. The zero rows will float down to the bottom. Okay? If we don't do this, then our solution will be out of order over here on the left-hand side. So notice if I just do one step where I don't swap any rows, I'll get 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0. Now I divided by 6 here, so I get 3, and I divided by 2 here, so I get 2. Okay, so this would suggest that our solution has C equals 3 and D equals 2. That's the polynomial 3x plus 2, whose second derivative is 0. Okay, so that is not a solution to our equation. But if we continued to go to row reduced echelon form, these float up to the top. We get 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 3, 2, 0, 0. Okay, now this tells us that our solution is, or a solution is 3x cubed plus 2x squared, right? The coefficients of x cubed and x squared. Now that is actually a solution, and in fact we could write down our entire solution set. Our entire solution set is 3, 2, 0, 0 plus C, whatever C is, a constant multiple of the vector 0, 0, 1, 0 plus D 0, 0, 0, 1. Okay, so I take these vectors and I insert 1s in the right spot, in the correct spots. CD, constant scalars. Now this solution set that I wrote down is equivalent, so this set of vectors here is equivalent to the set of polynomials that have 3x cubed plus 2x squared plus 0x plus 0 plus c times x plus d times 1. Okay, which we know are the solutions to this differential equation, right? I didn't actually ask you to write down this whole set of solutions. I say, what does this mean a solution to the differential equation is? So given your right-hand side here, you can read off that 3x cubed plus 2x squared plus 0x plus 0d is a solution to the differential equation. So even if you had just written this down, that would be fine. Now, some people just wrote down the vector 3, 2, 0, 0, or they wrote down a equals 3, b equals 2. That's great, but this is a vector. We have to go back and say, what does this vector represent as a function or as a polynomial? Otherwise, we haven't written down a solution to the differential equation. Now, finally, for this last problem, let's write down our augmented matrix. It's 4, 3, 12, negative 2, 7, 5 halves. Okay, the easiest way to do this, so I notice that I have a fraction here, so I'm not going to divide this in half and add them together. In fact, I'm going to multiply. I'm going to say row 2 equals 2 row 2 plus row 1, and row 1 stays the same. Okay, so I get 4, 3, 12. Now I get negative 4 plus 4 is 0. 14 plus 3 is 17. Now this times 2 is 5 plus 12 is also 17. Okay, I like to do an intermediate step when I get something like this, so I'm going to write down row 1 equals row 1, and row 2 equals 1/17 row 2. So 4, 3, 12, 0, 1, 1. Okay, now row 1 equals row 1 minus 3 row 2, and row 2 equals row 2. So 4. Now, so I'm going to take row 1 and I'm going to subtract 3 times row 2. So 4 minus 0 is 4. 3 minus 3 is 0. 12 minus 3 is 9. And row 2 stays the same. And then finally, I'm going to divide row 1 by 4. And I get 1, 0, 9 fourths, 0, 1, 1. Okay, so my solution is x equals 9 fourths, y equals 1.